You can't draw a control chart without taking some risks. What kind of risks? Essentially the risk of being wrong. This is what this particular problem is asking us to essentially incorporate. Suppose a manager must construct either a mean chart with known variation or a p-chart to monitor some process. When the process is in control, this is what I mean by risk of being wrong. The manager wants only 0.6%, less than 1% of samples taken to fall outside those limits when the process is in control. Oh, let's just, before we go any further, might as well stop and talk about this. This is what I mean a risk of being wrong. The process is in control. Theoretically, the samples should not fall outside the limits, right? Because the limits are supposed to, being within the limits is supposed to represent being in control. Oh, but the reality is, now maybe I can sketch this. Think of a control chart that's turned on its side. You know, normally they go from left to right, but I'm drawing one that's been rotated so that it's up and down. That means this would be its lower control limit, that would be its upper control limit. We took it and we turned it so that it's going vertically. Now, why did I do that? Because that is not how you generally look at control charts, because it's a lot easier this way to then draw a normal distribution. So I'm going to try to carefully sketch a normal distribution. Now, wait. What's the normal distribution represent? The normal distribution represents the natural variation in the samples when, in fact, this process that's being monitored is in control. Because we know its output will vary naturally. It will vary naturally if you're taking samples according to this distribution. Oh, now what we did is we set limits on the variation. That's the hard borders, the lower control limit and the upper control limit. And we said, you know, if any of the samples fall outside those limits, we're going to interpret that as a signal of danger, something's wrong. Well, the irony is that we basically amputated part of the natural distribution, right? We drew these limits, and these tails, right, are now cut off. And what they represent is exactly that. When the process is in control, right, the percent of samples that will fall outside of the limits anyway. Oh, nice vocabulary term here. This is what's known as a type 1 error. Okay, when the samples fall outside the limits, when in fact nothing's wrong, okay, they actually belong to the natural variation. That's also known as the producer's risk. Okay, why the producer's risk? Why is the type 1 error known as the producer's risk? Because picture what happens. A sample falls outside the limit. The person who's plotting the chart says, stop the process. It's outside the limit, something's wrong. You tear down the machine looking for what's wrong, and in fact there's nothing to find, nothing's wrong, okay? Because sometimes that actually happens. Right, so the producer is always running the risk of that by setting these hard limits. Now, what's happened here in this particular problem is that the producer is saying that the producer only wants that to happen not very often at all, okay? This is less than 1%, 0.6% of the time, basically, when you take a sample. All right, that means that, now the area of the curve that's been amputated, sort of excluded by the limits, that the area of the curve represents the proportion of times things would happen. So I'm going to convert that, and I need to be careful, to decimal place. 0.6% is 0.006. That means that if you could measure what I colored in yellow ink, it would be 0.006, you know, out of 1 of this entire shape, or 0.6%. Now, that would include both of these. Well, that means that if you were just looking at one of these tails, well, this is symmetrical. Even if maybe my drawing isn't exactly the same, this is meant to be symmetrical. A normal distribution is symmetrical. So if you took this and divided by 2, 0.003, that is exactly how much of the curve is right here, 0.003. Now, wait. We didn't even get to the end of this question, because what's the question asking? What is the z-value that should be used when calculating these limits, finding these limits? Okay, if you want this thing to be true, or 0.6% of the samples when everything's in control will fall outside the limits, what is the z-value? Yes, notice the charts that are mentioned at the beginning of the problem. I just read past it. The mean chart with known variation, or a p-chart. These are charts where if you look up the formula for the upper control limit and the lower control limit, they feature a z-value. The z-value is in essence determining where to place the limits. We want to place these limits here such that 0.003, right, or 0.3% of the natural distribution is here, and 0.3% of the natural distribution is here. Oh, I wish I had a table that, told me that if given I knew some, area of the curve, like what's the relationship to z. Wait a minute, I do have a table that tells me that. Given some area of the curve, what's its relationship? What z does it belong? That's a z table. That is a z table by definition. We're used to working with this z table in quality control because this is generally with control charts the handiest format. Oh, wait a minute, it's telling me that for an area of the curve, what z value belongs to it. Although I need to remember that this particular table, any z table, will tell you, what's this in here? What's different areas of the curve? Well, what in particular, what do you mean by area of the curve? Between the center of the curve and your limit, where you're cutting the curve. Oh, wait a minute. I know something about this curve, but I know that the tail that needs to be chopped off should only be that size, 0.003. Oh, wait a minute. The curve is symmetrical. That means that from here on over is half of the curve. So if I said 0.5 minus 0.003, this is just scratch work, I get 0.497. 0.497. Now what am I supposed to do with that? That means that in this chart that I want to draw, but I don't know what z-value to use yet, I want 0.497. That amount of area to be between the center and the limit. Okay, well, that's in here someplace. And when we find it, that will tell us what z. So what I need to do, in essence, what the task here is now that we have located what the area that the z table speaks in, we need to look in the body of the z table for the number closest to that. 0.497. So let's look. 0.497, 0.47, 0.494, 0.4968, 0.497. I found it way down here. 0.497 exactly. What z does that correspond to? Okay, trace it out. There's the first two digits, 0.27. What column am I in? All the way back up here. I am in the column labeled 0.05. That means that 0.497 corresponds to a z-value of 2.7, the first two digits, 5. Oh, well, actually, that's the answer. Z equals 2.75. How did I find it? I looked up that area, 0.497, and that is the z that it belongs to. If you drew up you calculated your limits, putting 2.75 in for z in that formula, then it would draw the limits such that exactly 0.6% of the samples would fall outside of the limits when in fact the process is actually in control. Oops, it happens. Now if you look at the next question, you see that it's an opportunity to practice this same process. It's virtually but not exactly the same question. Suppose a manager must construct either a mean chart with known variation or a p-chart to monitor some process. When the process is in control, the manager wants only, here's the difference. Let's try that same exercise again. Except this time the manager is willing to be wrong more of the time. 12.6% of the time the samples will fall outside these limits, when the process is in control. But again, it's still a question of fine. You need to draw your limits. What z-value should you use in the formula? I always draw a picture. helps me keep the numbers straight. We're drawing a control chart. There is this natural variation that's going to happen anyway in the samples. Ugh, not a very good sketch of a normal distribution, but it'll have to do. Of which, you can't avoid this, a certain amount of the natural distribution is kind of accidentally excluded by the chart. The type 1 error here, the risk of it, actually you could say the producer's risk, whoops, 12.6%. Okay, 12.6%, first off, that's 0.126 in z-table speak, changing the percent to a decimal, right? That's going to be the combined area in yellow here. All right, now, if I take that and I split it in half, I did that, I get 0.063. And I remember that that means that one of these tails is 0.063. I would like to track down the z-value that places the limit right there, but that means that I need to find this area in here because that's what the z-table is reporting in. All right, so I take the 0.063, it's just scratch work here, and I say 0.5 minus 0.063. I get 0.437. So this area in here is 0.437. That's all I need now to track down the z-value. Same exercise, go to the z-table, except we're looking for a different number now, 0.437. 0.4, it's going to be far higher up on the table than last time. 0.438, 0.437. There it is, just exactly. Okay, who does it belong to, so to speak? A z of, trace it over on the row, 1.5, that's the first two digits. Trace it up. What column? It says 0.03. Perfect, I just have to remember that. 1.53, 1.53, 1.53. Use a z-value of 1.53. When you're filling out the formula to set the upper control limit and lower control limit, use z equal 1.53. Why? So that exactly 12.6% of that natural sampling distribution will in fact be excluded by the resulting limits.